My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 274th International Physics webinar, and we have with us here today Dr. Manojendu Choudhury, Sir, Assistant Professor, Department of Physics, St. Xavier College, Mumbai, India, and he has already connected with us. So I'd like to welcome our speaker. Sir, good evening, and thanks for joining with us.
Good evening.
So
Thank you for inviting me here.
it's a pleasure, sir. So, dear student and viewers, I think you have already come to know the title of the today's International Physics webinar. Title is the what and how of compact objects and their emission. And our speaker is Dr. Manojendu Choudhury, Assistant Professor, Department of Physics, and Xavier College. And we can see that our speaker, Dr. Manojendu Choudhury sir, has completed his bachelor degree from Deshbandhu College, University of Delhi in 1995, and his MSc degree in IIT Delhi in 1997. And uh, uh, so he did his PhD in physics from Tata Institute of Fundamental Research in 2005. And he has a lot of research behind his career. So I think you will enjoy and learn a lot of things from this lecture. So please stay with us, and you can also join us by using the link. I will send the link in the comment section, and you can also ask the question by commenting. So, sir, it's your time. You can start your session.
Okay, thank you very much for that kind introduction.
My pleasure, sir.
Okay, so I mean, when we decided that I will talk about on this particular topic, I chose the title such that it is such a vast topic that if I miss out on anything, and if somebody comes up with a complaint that my favorite topic or a particular point was missed, I can always claim that it's a very vast topic, and I can talk about any small details and all, and it is a part of this particular header. So it was actually, I thought I'll be very clever in writing such a generic header, giving such a generic title. But let's see. I hope we are able to do some justice in today's interaction. Okay, and maybe I hope that that you return with something more gained after this lecture. Now, compact objects. Okay, so you should start thinking the moment the words come. When we talk about jargons in scientific literature or in scientific communication, the jargons have a very precise meaning actually. Of course, it takes time for the jargon to develop. But in general, what happens, when we talk colloquially, say in English or any other language, we use words with some poetic license. But when it comes to science, you cannot have that poetic license. So we should think about what is compact object. When we are looking at compact objects, when we come across the words like compact object in literature or in science communication, what does it actually mean? So let's go through that particular meaning of compact object first. Okay, now if you go to the dictionary and look for the meaning of the word compact, then this is the general meaning that you get. I'm taking this from dictionary.com, but I'm sure that other dictionaries will have very similar set of meanings attached to this object. Joined or packed together, which are, compact means close and firm together. Things are arranged in a very small space. Sometimes compact means solid, but as we'll see today, that compact doesn't necessarily confine itself to solid. You can have liquids and gases also. But one thing that is the most uh, informative in this whole series of words which try to give the meaning of the word compact is the word dense. Okay, so what it means is, now we are going towards a more precise definition of the word compact. So we should look at the concept of density, which I'm sure all of you have know from middle school level. You, whenever you go through any discourse on science in the middle school level, you definitely come across the concept of density. And when we look at density, of course, the unit is mass per unit volume. In terms of SI units, we say it is kilogram per meter cube. Now, let's look around us, look at the natural world around us, and let's try to get an estimate of densities of various things that we are dealing with. So, let's start with the least dense of all the entities that are around us, and we'll talk about air. Okay, so air density has is of the order of a kilogram per meter cube. So if you take a cube of dimension 1 meter on every side, then it should weigh around a kilogram, little bit more, little bit less, depending on the temperature. As this picture shows, hot air rises, cold air comes down, and you have convection currents due to the different levels of pressure and density and temperature. Of course, all these are interconnected entities, interconnected properties. And immediately you should come to know, or rather come to realize, that when we are talking about the mean density, it doesn't really mean that all throughout your air volume the density is same. No, you can have some places where the density is more, some places the density is less, and if you have a mixture of gases, and obviously different gases may have different densities depending on the temperature and pressure of each gas. Okay, but what is most important out here is, please look at this number. For the next few slides, we will be looking very carefully at the numbers. Okay, so here it is of the order of 1 kilogram per meter cube. Now, let's look at the next dense entity that we have, the liquids. Typically, water has a density of 1,000 kilogram per meter cube. Of course, in this picture, you can see that you have different layers of different colored liquids, and the reason why they are separated is because their densities are different. So, again, we are talking about a mean density, but it doesn't really mean that all of them have the same density. But today, in throughout this interaction today, we will just talk about estimate. We will not talk about very precise numbers. We will talk about the back of the envelope calculations. Okay, now, so we are moving 3 orders of magnitude in terms of density. Okay, 3 orders of magnitude, mind you, not factor of 3. It is not 3 times, it is 1,000 times we are talking about. 3 orders of magnitude means 10 raised to 3 we are talking about. Okay, now let's look at the solids, the rocks that make the earth's surface around us, and they are definitely more dense than the than the liquids, and that is why most of your rocks, even if they are porous, they sink into water. Okay, there are very few very special rocks which float on water. Okay, they are very rare species of rocks, and the density is few factors more than the liquid phase. Okay, so please look at these numbers very carefully. From gas to liquid, when we moved an order of 3 orders of magnitude, whereas from when we are moving from liquid to solids, we are not actually moving in the order of magnitude, we are moving by a few factors. Okay, factor of 2 to factor of 6, 5 or 6 or something like that at most. Okay, next we look at the metals, which are actually very dense. Okay, so supposedly very dense. Okay, so let's look at this metal. I hope all of you recognize that we are looking at a lump of gold. Okay, and it is nearly the order of 2,000 kilograms per meter cube. This is the density. So you can say the rocks and the gold and other metals, they are more or less of the same order of magnitude when it comes to the density. Okay. Now, if we look at the atomic nuclei, okay, so let's take the same element gold and let's look at the atomic nuclei. We are looking at a density which is of the order of 10 raised to 17 kilogram per meter cube. Of course, when it comes to these numbers, unless we practice, we do not understand the significance of these orders of magnitude. So I will request all of you to spend your time thinking about these orders of magnitude changes and try to develop an estimate of all these orders of magnitude. Okay, so here we are moving by an order of magnitude of 14. Okay, 10 raised to 3 to 10 raised to 17. So think about it. Okay, so and this is kind of the densest entities that we can look around the nucleus of the atoms. Of course, it also tells that most of the atom is actually vacuum. You have nucleus and then huge amount of vacuum with some electrons sprayed in it. Okay. Now, this is the range of densities that we find in the entities around us that we can feel and touch: air, water, solid, and what we do not realize but we infer from the experiments, the nuclei of all these atoms. Okay. Now let us look at the cosmic bodies. But before we go to the cosmic bodies, I just wanted to share this beautiful picture of the Earth. And the speciality of this picture is that this is one long exposure. Okay, otherwise all the images of the Earth that you find is normally many exposures taken over many days perhaps, and they are stitched together. But here this is one exposure. Okay, and I love this image, so I just wanted to share this with you. And it was, of course, this image was taken by the Russian weather satellite Electro 1. Okay, now let's look at the Earth first and look at the density. The density is of the order of 5,500 kilograms per meter cube. This is roughly the order of the solid matter that we see around us. Okay. Now, of course, the density of the whole Earth everywhere is not the same. Places where you have water, it will be less. Places where you have the land, it will be more. And of course, the core and the mantle, they are definitely much, much more dense. Okay. But still, it is more or less of the same order of the solids that we see. Let's look at Jupiter. Now, this is again a beautiful image of Jupiter where this shadow is actually the shadow of one of Jupiter's 4 Galilean moons, Io. So this is the Io's shadow on Jupiter. You can say this is a lunar eclipse, a solar eclipse on Jupiter due to one of the 4 moons. Okay. Now, coming back to the density of Jupiter, it is of the order of 1,000 kilogram per meter cube. Mind you, Jupiter is much larger than the Earth. The radius is of the or 10 times more, and so it is approximately, volume is about 1,000 times more. 1,000 Earths can fit into Jupiter. It's huge in terms of volume. But the density is less, and that should immediately tell us that it is more gaseous in nature than solid. Okay. Now let's look at the sun. Now the fun part, look at the sun's density. Sun's density, if I take the mean density, that is the total mass divided by total volume, then again it is not a very dense object compared to the Earth or Jupiter. Okay, but if you look at the different layers of the sun and go to the core, which is about, the radius is about 20-25% of the solar radius. Okay, so volume wise it will be about, you know, zero point 0.2 cube is 0.008. Okay, so it is of the order of 0.8% of the solar volume. Okay, now in this core, this is where your nuclear reactions happen. It is the densest region in the sun. Okay, otherwise as you go away from the center, the density decreases and the nuclear reactions no longer happen. Okay, so now if you look at it, the density is of the order of 150 into 1000 kilogram per meter cube. Okay, so we're moving from nearly 1.5 to 150, a factor of 100. Okay, an order of magnitude 2 increase in the density of the core. So you can see within the solar object itself, the sun itself, we have seen such a drastic change in the density level. Okay, but again, look at the number, it is only 1.5 into 10 raised to 5. Whereas when it comes to the atomic nuclei, it is of the order of 10 raised to 17. And this is of the order of 10 raised to 5. Okay, so now, not spending too much of time, let's look at what are the densest objects that we can see in the universe. Okay, before we go to the densest objects, let's see how are they formed. The densest objects, the compact objects, which are referred to are normally the white dwarf star, the neutron star, and the black hole. Of course, black hole you can't see, so there's nothing out here. Okay, of course this picture is also not drawn to scale. Okay, this is just a schematic. So what you have out here is that you have to understand that all the stars have a life cycle from birth till death. Okay, now they are born in a stellar nursery in giant molecular clouds, where you have where the cloud collapses and forms millions of stars wherever gravity takes over and is greater than your kinetic pressure and radiation pressure. Okay, and you have sustained nuclear reactions happening in the core. Okay, so once these stars are formed, then they live their lives. A typical star like sun lives a life of 10 billion years. A very, very massive star of the order of 30 or 40 solar mass will die off in less than a billion year, a few 100 million years. Of course, it's a long time compared to our lifetime, but compared to the 10 billion years of the sun, it is nothing. Now, these stars go through a phase of where the core will collapse into more dense region and the outer envelope will expand. Okay. Now, when it comes to the relatively smaller stars like the sun, they form a planetary nebulae where the core collapses to a star called a white dwarf star and the outer envelope is expelled out. When the star is much, much more massive, they go through again the red supergiant phase, and then the core will collapse and the outer shell is thrown out in a supernova. Okay, and depending on the mass of this core object, if it is less than 2 solar mass, it will form a neutron star. If it is more than a 2 solar mass, it will form a black hole. Okay, now these endpoints of the stellar life, the white dwarf, the neutron star, and black hole, these are known as compact objects. Okay, let's see why. Okay, before let's see why, this is just a diagrammatic evolution where you saw we are looking at the HR diagram where the x-axis gives me the temperature and the y-axis the luminosity, and this is the main sequence stars where all the stars live are in their life But a star like the sun will evolve. Once they start evolving after 10 billion years, the sun is 4.5 billion years old. After 5.5 billion years old, again more, it will move away and follow this kind of a trajectory in my HR diagram, and then it will come and shrink and become here. Mind you, this is luminosity. Luminosity is also a measure of your size, of the mass, and hence the size. Okay, so what happens out here? Here, this is my size. Here, this is my size. This is my luminosity, and this is my luminosity. Okay, and also this is my temperature now, and this is what the temperature will be. So mind you, in the x-axis, the temperature is increasing as we move towards the left. Okay, so this is how a typical sun-like star evolves. Other stars which are here, the more massive stars, they evolve in this direction, and then they become neutron stars, which are not shown in this diagram. Okay, now let's look at white dwarf stars. Okay, so a white dwarf star has a density of the order of 10 raised to 9 kilogram per meter cube. If you remember, a couple of slides back, we saw that the density of sun, average mean density, was about 1.4 into 10 raised to 3 kilogram per meter cube, whereas the density of the core of the sun was 150 into 10 raised to 3, which is 1.5 into 10 raised to 5 kilogram per meter cube, and white dwarf star has a density of 10 raised to 9. So a solar core has 10 raised to 5 kilogram per meter cube, and a white dwarf has a typically density 10 raised to 9. We have moved 4 orders of magnitude, 10,000 times the density has increased. And of course, this is an example of white dwarf, Sirius A and B. This is Sirius A is a main sequence star, and this small one, Sirius B, is a white dwarf star. Okay, typically the size of a white dwarf star is the size of the Earth. Okay, 5,000, 6,000 kilometers is the radius, and the typical mass of white dwarf is say 1 solar mass. So you can imagine the whole mass of sun confined to a size of the planet Earth. That is the density of a white dwarf, and that is why it is called compact. But of course, we will see that is not the only criteria for calling an object compact. Let's see why. Now let's go to neutron stars. Okay, neutron stars which are observed can be of two types. Okay, one is accretion powered neutron star, where this neutron star here is accreting matter from the environment, which is now, when I say a neutron star's environment, if it is accreting matter, it has to be in a binary system where it is getting matter from the companion star. And if I see an isolated neutron star, then I can only see it when it is it's rotating such that the magnetic axis and the rotation axis are not in the same direction, and hence when it rotates, the magnetic field will point towards and away from us in a periodic manner, and these points, the poles of the magnetic fields, they will be the hot spots, and we will be able to see them. And these hot spots are very bright because all the charged particles are accumulated along the magnetic lines of force, and the magnetic lines you can see at this region, they are far away, and at these points they are extremely close together, extremely dense, and hence we see the emission of hot spots from these, and these are normally in the radio band. Okay, so if you look at these isolated neutron stars in the radio regime, we see pulsations of light, and they are known as pulsars. Whereas these objects, when they're accreting matter from the companion star, then the luminosity is happening due to the matter that is falling in. Okay? And these are known as accretion powered neutron stars. Now, the theoretical model of neutron stars are still being debated in the scientific community. Okay, it's a very, very active field of research where people are trying their best to get a complete comprehensive theory of the neutron stars and define the equation of state of the matter out here. But there are many competing theories out there, and given the present scenario of observational data, we cannot distinguish between these competing theories. Okay, so these are different theories, but if you look at it, then you will see that for a mass of say 1 to 1.5 solar mass, at most we can see 2 solar mass, and the heaviest pulsar is of the order of 2.08 solar mass. Okay, so these objects having a mass ranging from 1 to 2 solar mass are defined over a radius of 10 to 14, 10 to 15 kilometers. Okay, so now understand that when we were talking about white dwarf, one solar mass confined to the size of the Earth, and here one solar mass is confined to the size of a sphere of 10 kilometers. Okay, and that gives me a density of the order of 10 raised to 17 kilogram per meter cube. And immediately you should remember that this is also the order of magnitude of density of atomic nuclei. So neutron stars have the same density that of an atomic nucleus. Okay, now this, please remember these numbers. These are very, very careful, extremely important numbers that we should remember. Okay, now let's look at the object which is considered to be the most compact of all, which is my black hole. And I think from the given popularity of this terminology and this concept, we are more or less all aware of it, that black hole consists of an event horizon such that all the matter that has collapsed below this radius is no longer visible to us, because even light cannot escape. Okay, today I will not talk in detail about history of black hole, but the first concept of black hole was actually given in 1780s, late 18th century. But today we understand black hole significantly better, and we will see why exactly. Okay, now this point, the center of the black hole, is a singularity, and we really do not know what happens in the singularity. Okay, what we know is that this size of this black hole, which is not rotating, is known as a Schwarzschild radius. Schwarzschild was a person who first gave the solution to Einstein's Fields equation. Okay. And of course, he was involved in a battle in First World War when he gave this solution, and then he was feeling sick, ill, and he returned from the battle, gave his solution and everything, and then unfortunately collapsed and died. Whereas his sons, his family, they moved to USA, and in 1930s and 40s, one of his sons gave a, played a very important role in developing the nuclear theory of stellar composition. You can say the nuclear astrophysics. So if you look at Schwarzschild, if you look at the mention of Schwarzschild, you should be careful whether it is about the black hole solution of Einstein equation, or is it about nuclear astrophysics, because they are father and son. Okay, now what happens is that if we want to define the density of black hole, then we should be very careful of what we are talking about, because we simply don't know how is the mass distributed inside? As we saw, even in the case of sun, the core was 100 times more dense than the outer shells, or the the mean density. Here we simply have no idea whether this black hole has any mass, or it has completely collapsed to singularity, or what is happening inside. But still, for the sake of consistency, if we define that density is total mass divided by total volume, and we come to the concept of the mean density of a black hole, it's with this very big caveat. Let's look at the numbers. So the radius, please pay very keen attention here. Radius of a black hole is proportional to the mass of the black hole. So the volume of the black hole is proportional to the mass cube of the black hole. And so the density, which is mass upon volume, it will be m upon m cube, is actually a function of 1 upon m squared. Okay? So if I have a black hole of 1 solar mass, then its density will be this particular quantity, 3c raised to 6, where c is the velocity of light, and 32 pi g cube m squared. Mind you, 1 upon m squared is a proportionality of change of density with mass, density of black hole with mass. Okay? Now, if we take the sun and collapse it into a black hole of this, then this radius comes out to be 2 kilometers. So you see, immediately you see that neutron stars, which are of the order of 1 solar mass, will have a radius of 10 kilometers, whereas a black hole of 1 solar mass will have a radius of 2 kilometers. And if you look at the density of neutron star was 10 raised to 17 kilogram per meter cube, for a 1 solar mass black hole it will be 10 raised to 30. It is extremely dense. But as we understand today that a 1 solar mass black hole perhaps doesn't exist, or very unlikely to exist. But of course, if you observe it tomorrow, then I have to take back my words. But as of today, we understand that a black hole should exist at least of 3 solar mass. And the moment we move to 3 solar mass, the density, the mean density of the black hole becomes 2 raised to 18, which is nearly the order of the density of the nucleus or neutron star, because density is proportional to 1 upon m squared. And the moment we go to a supermassive black hole, AGN, which is of the order of 10 raised to 6 to 10 raised to 9 solar mass, then the density of that black hole is 18 kilogram per meter cube. Okay, now if you remember, the density of water was 1000, density of air was 1.5, and here I have 10 raised to 9 solar mass black hole has a density of 18. So the density has decreased enormously. But what has happened is that the mass is huge. Now please understand, if I have a star of 30 or 50 solar mass, it cannot exist for more than 300 or 500 million years. But a black hole of this order exists for billions of years. So the reason why it exists for billions of years is actually that its density is decreased, but the mass is enormous. So now you have to realize that when we are talking about compact objects, it is not just mass, it is not just density, it is a play of both density and mass. Okay, and so density, mass are not the only criteria of compactness. To have a proper idea of compactness, we actually need to understand general theory of relativity, and come to the concept of space-time singularity. Ah, okay. So, when I look at the criteria of compactness, there are two ways to look at it. One is look at the density and mass, and the other is look at the space-time curvature. Okay, this interplay of density and mass is actually explained better by the space-time curvature. All right. Now, I assume you know about space-time curvature, or if you don't, I have seen that in your series of lectures, there are many excellent lectures about general relativity and black holes, where a lot of details are being discussed. So I will just say that when it comes to space-time curvature, we are looking at actually a four-dimensional curve, which we cannot represent on a two-dimensional surface. So here we are considering three-dimensional space in this two-dimensional plane, but actually this is three-dimensional. And here, this is my time axis, okay? So at any given point of time, if I'm here, then I can be influenced by any event in the past which happened in this cone. Okay, and I can influence any event given in this particular cone, and the surface of this cone is given by the speed of light. Okay, and this is a hypersurface because simply because we cannot see the whole of the surface. Now what happens in a black hole is, you have to understand very carefully that this cone, which tells me how much I can influence the future, it also tells me how I can transmit an information, because I influence the future by transmitting some signal. Okay, now you look at it, this particular cone, when it is here, and mind you, this is the time axis. Okay, and this thing is my space axis. Okay, so I'm an observer here, this is the time which is go. Now if my, okay, with time my eyes, my observation is point is moving here. Okay, because time never stands still. So if I'm here now, next instant I'll be here, next instant I'll be here. Okay, so the observer is moving along this axis, and the object, if a particle is falling along the onto this event horizon, okay, this is my event horizon. Now suppose this guy is falling into like this, okay, I mean this path or this path, then what happens is that light moves along this surface, so it is moving along this surface and it reaches here, the observer. But because of the curvature of space-time, moment it crosses the event horizon, these light cones, look at the cones, these cannot move here, are directed completely inwards. This is a boundary condition. So if the object is at the boundary, the light will move along this curvature, it will not come out, and anything inside will all fall inside. Okay, so it's like as if, the time axis has taken the property of space axis. Okay, in space you can go back and forth, in time you cannot go back and forth. Here, things become very, very complicated. So that is why light cannot come out of a black hole. So this is the criteria of compactness actually, that what is the curvature of space-time. And if you look at density, only density will not help us to understand. We'll need the concept of matter, total amount of matter, and density. Okay, so this is the Schwarzschild solution out here, which is my three-dimensional solution of space-time of an object here at the center, which doesn't have any angular momentum. Okay, and you can see that depending on the mass, If I have a very massive object like a supermassive black hole, then this is the nature. And if I have an object like a black hole out here, a stellar mass black hole, then this is the nature of the space-time continuum. Okay, now let's see what we have seen: white dwarf, neutron stars, and black holes. Okay, now let's, I don't know, my laptop is reacting very slowly sometimes, it's not moving ahead. Let me just see what is the problem. Because now I'm coming to the second half of the lecture, which is the emissions from these sources. Okay, now we have some idea what these sources are like, what are the physical properties of these sources. So let me see. Just give me 1 minute or something. You know. Okay. So I hope this will continue now without any hassle, any further hassle. Okay, so now look at the emission. That is, what is the radiation we are, how do we know about these sources? Okay, so quickly looking through a dwarf novae of the cataclysmic variables, which comprise of a white dwarf star, which is accreting matter from a companion star. Okay, and this matter is falling in, and of course we can see this matter in optical and ultraviolet light. What happens out here is that there are moments when there is an outburst in this accretion disk, and that is known as dwarf novae. Okay, dwarf novae, because nova is also a phenomena that is seen in case of white dwarf stars. The difference is that when in a case of dwarf novae, the luminosity increases by a factor of 10, whereas in case of a classical novae, the luminosity increases by a factor of million. Okay, so these objects, when they interact with a companion star, which is, then they can have enormous amount of variability, and very interesting physics can be learned about these stars. Okay, at the same time, I just like to mention that although we talk about neutron stars as pulsars, but these white dwarfs also show pulsations. Okay, they also have a magnetic field, and the matter is aligned along the magnetic lines of forces. So it is a very, very interesting branch of study of cosmic sources, these white dwarfs. Neutron stars, I will not go through too much of details, so I will just skim through these slides. But you should be aware that the order of the sizes and the different uh, layers of the stars which are there, and you have different kinds of nuclei and the in these different layers. Of course, the rotation of the neutron star causes the rotation of the electric current. It causes the electric current in the different layers of the star, neutron star, and that causes the very strong magnetic field. A neutron star can have a magnetic field of the order of 10 raised to 10 to 10 raised to 13 or 14 Gauss. And the extreme form of very strong magnetic field neutron stars are known as magnetars. They can have magnetic field of 10 raised to 14, 10 raised to 15 Gauss. Okay, so the reason why we see pulsation is why it's very well clearly shown in this particular simulation. So you have your rotation axis and the magnetic axis. They are not confined. They are not in the same direction. Okay. And of course, this is a statistical distribution of the total number of neutron stars and how many of them are X-reactive, how many are pulsars, how many are in the binary systems. We will discuss them sometime later, perhaps, when we talk about more in detail about extra astronomy. Just understand one thing, that if we take a compact object and a companion star, then these red lines, they provide the potential surfaces. Okay, if your mass does not fill up the potential well in which they are confined to, if it is confined to this particular object, it is the potential well of this object. If it is confined to this object's potential well, then it is confined here. Okay, so this is the potential well given by this, and the potential well of the compact object is given by these lines out here. Now you can have the whole Roche lobe, the potential field, filled up by this star. Then what happens? The mass of this star fills up here and it flows into this particular potential well. And this is the accretion process that is happening out here. Okay, it might happen that the mass doesn't fill up the whole potential well, but few particles escape through winds. And when they are escaping through wind, they escape in all directions. Some small fraction is caught up in this, the potential well of this object. And then also accretion takes place. They are known as wind fed accretion. Okay, or else when you fill up the Roche lobe, that is this particular potential well, and the mass flows here, it is known as Roche lobe overflow accretion. Okay, now let's look at it, this picture again, that when a particle falls in this well, it is going down in the energy level, so the particle is losing energy, and that energy is expelled or radiated. Now look at the radiation of that energy. Okay, so if we have nuclear burning, then if mass m is burnt, then the energy is given by 0.007, that is 0.7% of mc squared. That is, if m mass is burnt, then the rest mass energy is this much. Okay, and 0.7% of it is given out in terms of energy. So if I have 1 gram of matter, and the whole 1 gram of matter goes to nuclear fusion, then it will produce 10 raised to 18 ergs from 1 gram. If we have same 1 gram of matter falling into the gravitational potential of a compact object, especially a black hole, then it can give out 10 raised to 20 ergs. Okay, the efficiency of nuclear burning is far less compared to accretion when it is in terms of the energy lost per unit mass. Okay, so in that sense, accretion is far more efficient in converting the rest mass energy into radiation, and this happens in this case of the compact objects. because of the gravitational well potential. Okay, and that happens again due to your space-time curvature, because Einstein's field equation equates the curvature with the energy of the system. Okay, so this is another depiction of wind-fed accretion and the Roshlov accretion. Let me go quickly. Let me just measure one very important thing. So matter, we are talking about matter falling into the compact object, but mind you, matter falling into the compact object cannot be explained in terms of Newtonian potential. Okay, because in Newtonian potential, what happens, the moment I have an angular momentum of the infalling particle, then there are two potentials working. One is the gravitational potential, the other is the effective potential due to the angular momentum, and the resultant is this particular potential. Now this particular potential has a minima here, but then it increases, and you see even a particle with positive energy will get rebounded here. Okay, so I have one component due to this angular momentum, the total potential, the other component due to the gravitational potential. Okay, and the sum of two ensures that as I go towards r equal to 0, my total potential becomes infinite. And so the matter is always reaching a minimum distance and then unable to penetrate that. Whereas when I look at the general relativity, then in addition to my angular momentum and the gravitational potential, there is a third factor out here. Okay, there is another parameter acting out here due to the space-time curvature, and this is a negative potential. As a result, my total potential becomes negative and my matter can fall in. Whereas if I follow the red curve, it is only Newtonian, my matter cannot fall in. Okay, now this is something that you can talk about. These are my equipotential surfaces. Now you see, if I have two stationary objects, these are my equipotential surfaces, and this is a point of unstable equilibrium where the resultant force due to gravity due to these objects is 0. So it is an unstable equilibrium point. A slight nudge here and or here will push the particle into this potential or this potential. The moment you have an angular momentum of these, then we, in addition to these unstable equilibrium point, we have more equilibrium points coming out. So this was my L1, the unstable equilibrium point. L2 and L3 are again points of unstable equilibrium where my resultant force is again 0. Here my gravitational potential is balanced by the centrifugal force of the system. Here also the gravitational force is balanced by the centrifugal force of the system. So we have 3 points of unstable equilibrium and 2 points L4 and L5, such that these objects, the two bodies and this object, they form an equilateral triangle. These L4 and L5 are points of stable equilibrium. They are the stable Lagrangian points. Okay, and we have started making use of these stable Lagrangian points when it comes to developing satellite observatories. Okay, so these are the formula of the stable equilibrium point. We can discuss them more in later. Okay, so this is how the object actually, the whole system looks from a frame of reference of rest. Okay, so these two objects are these two stars, you can say. One is a compact object, another is the other companion star, are my two stars. These points are the points of equilibrium. Okay, and matter falls from this object to here through this inner Lagrangian point. Okay, and hence what I have is we have this concept of different kinds of binary stars, and depending on the nature of the binary. We can have a binary system where I have a common envelope where a lot of matter is falling from one from the other, and I can have a semi-detached binary where one star is throwing out matter into the other, or we can have detached binaries. Okay, now depending on these nature of transfer, I'll have different kinds of radiation, and also the stellar evolution will be guided by this kind of mass transfer. Okay, so when it comes to accretion, we have to understand that the two main kinds of objects which shows accretion are, one is the X-ray binaries, where I have a binary system of stars, and the other is active galactic nuclei, where it is the center of the galaxy, which is of the order of 10 raised to 6 to 10 raised to 9 solar mass, and it is accreting matter from the companion. Okay, and here the infalling matter gives out radiation, and that is what we observe. Okay, and when the matter is being accreted into the compact object, because of the conservation of angular momentum, it forms an accretion disk and it spirals in. Okay, and when this matter falls in, then the gravitational energy lost is radiated out, and what I see is my luminosity due to accretion, which I can write in terms of mass loss out here, and this is my gravitational potential of the compact object, and this is the mass loss from the companion star. Okay, and this particular quantity 2 gm by r is again a measure of my, I can replace this r by my Schwarzschild radius, and what I get is eta m dot c squared. Okay, so this is again how I can compare with eta as the efficiency, where and I can compare m dot as the rest mass that is falling in. Okay, so what you can assume from here is that the amount of matter that is falling in, if we keep on increasing to infinity, then I should get infinite amount of light. But that doesn't happen, because light, after a certain density of radiation, starts behaving like a gas of photons. It's actually always behaving like a gas of photons, but it becomes very significant such that the photon gas will now be working in tandem with the gravitational force, and gravity balances out the radiation pressure. Okay, the photon gas becomes so dense, and that condition is given by the Eddington luminosity. So Eddington luminosity tells you that if my compact object is of a particular mass, then that is the maximum amount of light that I will get, and this light is, if I convert it in the radiation form of electromagnetic radiation, then I'll see it falls in the X-rays for X-ray binaries, and of course X-ray and ultraviolet and optical for the active galactic nuclei. Okay, so we need to appreciate that we have an accretion disk, and that accretion disk can behave like a black body. In that case, we can treat the accretion disk as a thermal emitter and measure a temperature of the accretion disk. But there are other processes also working out there, and hence the thermal disk is not the only physical mechanism working out there. We have bremsstrahlung working, and also scattering by Comptonization is also working out there, and hence the whole physics that is happening is very, very complex and very, very challenging. And to understand that, we look at the spectrum of such objects. Okay, and then try to explain this spectrum by modeling the theoretical paradigms that we have. Okay, and of course the emission, the amount of matter falling from the companion to the compact object can vary Sometimes it increases, sometimes it decreases, and that is why the emission of from the accretion disk also varies. Okay, and that makes this a very, very interesting and challenging field of research. If you look at the physical separation of these compact object binaries, then this is a very, very interesting figure. You see the scale given by Sun and Mercury out here. Okay, and now look at how close these binary systems are. Okay, their binary periods are of the order of few days. Okay, this is of the order of Cygnus X1 is 5 days, and this is of the order of 35 days, GRS 1915. And then you have binaries which are of the have the order of 1 day or maybe less than a day. Okay, so that is how close two stars can be, and that is when they accrete matter and they emit in X-rays. And before I end, let me just tell you that the most interesting feature of these sources is that when matter is falling in, whether it is a quasar with a black hole of 10 raised to 6 or 10 raised to 9 solar mass, or a stellar mass black hole, 10 solar mass or so, when matter is falling in, all of the matter doesn't fall in. A significant chunk is thrown out in the form of jets. And this is a very, very interesting phenomena that we study. And it is, we still don't completely understand the mechanism of it. Okay, it's an active field of research that what is guiding these objects to throw the matter out. Okay, now as I end, let me tell you that X-rays, when we are looking at X-rays from this source, we cannot look at this source from the surface of the Earth, simply because if you look at the atmospheric opacity, then the opacity goes down and the atmosphere becomes transparent only in the visible spectrum, few narrow channels in the ultraviolet spectrum, and in the radio spectrum. For all other wavelengths, our atmosphere is opaque. Okay, and hence, if I want to observe in the X-rays, I have to build satellite that goes above the atmosphere, and that is why we have satellite observatories. Okay, of course, for optical and infrared observation also nowadays we have satellite observatories, and the reason is that the atmosphere, although it allows light to fall in, it also creates a lot of distortion, and by going above the atmosphere, even in optical and infrared regime also, we will get a much better resolution. Okay, and let me tell you that this is a very recent development. Last about 2 years, 2.5 years back, the first direct imaging of a black hole was made using the Event Horizon Telescope. Okay, I have seen that in your series of lectures, there has been people have talked in much detail out here. So I will not talk in detail. I just mentioned in the passing that this is a very, very significant observation. But mind you, this observation is done in radio. Okay, so the actually this image that you see is not orange; it is radio color. Okay, and it is using telescopes scattered all over the earth so that the whole baseline behaves like one lens, and that is how you're able to resolve this particular object. Now there are other ways in which you can observe these black holes. Last few years, very interesting development. Again, there has been talk on these topics, so I'm just mentioning them. The gravitational waves is such a messenger which tells us about black holes and these compact objects. Okay, so this is the fundamental mode of gravitational wave that we see. Okay, I will end this talk by saying that if you are interested, you can actually get onto this particular branch of research in extra astronomy, where you have all the observatories data available in the internet. So this is one website where you can make use of the data available here, data and the software. And Astrosat is another observatory, which is Indian observatory, launched in 2015, and that also has its own website and software way and the database from where you can observe all these sources and you know do research on these objects. Okay, that's all I have to I thought I'll share today. Thank you for listening to me.
Thank you, sir, for your excellent lecture. So we have a few questions. So if you allow, we can start our discussion.
Yeah, sure,
The
definitely.
first one, can black holes provide us some knowledge about quantum gravity?
Well, that is a branch of quantum gravity we are looking at. We are hoping that it does. Someday we'll make some breakthrough, but right now it is a field of active research where breakthroughs are expected. We are waiting for it. Until then, we don't have much information, but yeah, we hope that someday in near future we will have something.
Okay, so thank you. There is another question. So do fuzzballs in string theory give the true quantum description of black holes?
This is again your it's an extension of the previous question. You see, when it comes to anything about string theory, we are actually quite far from any observational feature of string theory right now. Okay, so maybe by the time you guys reach my age, maybe you'll have something.
Okay, sir. So thank you again. So in your last page, you have shown some link of research. So
Yes.
if any student want to uh, do research in this field, what he or she need to do? Just go that link and download that software and can analyze that data. Or
Yes. In principle, absolutely yes. Anybody can do that.
okay,
Okay.
okay,
You but maybe if you start from scratch, you'll take a lot of time.
mhm,
If you ask someone who knows things, okay, then you'll get guidance and you can do. But sitting from your home, definitely you can do the research.
okay,
That's all that I'll say.
okay,
It's possible. Anybody in the world can do that, and we do that. We have done that.
okay, okay, sir. So
Yeah.
thank you. So thanks again, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for giving us time. So bye
It
for
was my
today.
pleasure.
Good night, sir.
Good night.